The experiment takes place inside this metal tube, with a super hot filament firing electrons at the slits. After passing through the double slit, electrons strike a detector screen, which produces these green dots.
At first glance, you would expect that for classical particles you would just get the addition of the two distributions. If you actually do it, there's an enormous surprise in store for us.
Instead of the distribution we'd expect from classical particles, electrons produce an interference pattern.
Electrons making an interference pattern. How is that possible?
Maybe the electrons are bumping into each other and repelling.
But how would that create an interference pattern?
What if we fire the electrons at the screen one at a time?
Electrons? One at a time?
Like classical particles?
Yes, like we did with the tennis balls.
Then they should form the same distribution the tennis balls did.
Should they?
If you were thinking of that wave as being built up out of many electrons, then surely the wave is gone, and surely the interference pattern must disappear.
The signal of the electrons hitting the detector screen is transmitted to a computer. The left image shows the electrons striking the screen individually. The right image reveals a pattern that is built up over time. Incredibly, after a large number of electrons hit the detection screen one at a time, they still produce the same interference pattern. So individual electrons behave like particles in arriving at specific spots on the screen. They also seem to behave like waves in building up an interference pattern over time. This shows that electrons have a dual nature. Physicists call this nature the wave-particle duality.
It's always amazing that we can actually see something that is a quantum mechanical effect on a physical screen in our lab. It's very rewarding to be able to actually do that, and it's a lot of fun.
And really excited about the double slit and what we can do in addition to what we've done so far.
You can look at this and you start pondering, what is causing this?
To explain the behavior of electrons, we need the idea of a wave. We need the idea that a wave can pass through two slits at once. So certainly there's something wave-like about electrons. There's also something particle-like.
So the electron is both a wave and a particle.
In some situations, an electron behaves like a particle.
In other situations, behaves like a wave.
Wave and particle behavior together.
You might think of it as a split personality.
Like us.
What do you mean?
You're not separate.
In the world of classical physics, we are separate.
In the subatomic world, we're two aspects.
Of the same object.
Yeah.
That's wave. Particle.
Duality.
It takes a while to get used to it. It's not easy at the first sight to understand it, but as you learn more and more, it's just amazing, all these possibilities.
Since it behaves like a wave, an electron has a wavelength. This wavelength is called the de Broglie wavelength. It's related to the electron's momentum by this equation. The symbol h is a universal constant with an incredibly small value. It's called Planck's constant, after German physicist Max Planck, who discovered it in 1900.
Are you enjoying the ride so far?
It's pretty crazy.
Welcome to quantum physics. I should warn you, it's only the beginning.
Remember Thomas Young's double slit experiment?
Yeah, it showed that light produces an interference pattern.
Right.
So light is a wave.
Right again. But what happens if we turn down the intensity of the light?
Like we did with the electrons.
Exactly.
At Brown University in Providence, Rhode Island, researchers are performing the double-slit experiment with light. They have very sensitive detectors that can detect light even when it's extremely faint. When the intensity of the beam is turned down, we see that light hits the screen as individual, localized particles. This provides strong evidence that light is made of tiny bundles of energy called photons. The energy of a photon is equal to the product of Planck's constant and the photon's frequency. The higher the frequency of a photon, the more energy it has. After many photons hit, the same interference pattern appears on the screen. So like electrons, light exhibits wave-particle duality.
When we study light, it can be a wave, completely a wave. And then we change the experiment and it looks entirely like a particle.
So now we have light and electrons on the wave-particle duality list.
That should do it.
Not quite. Wave-particle duality isn't limited to light and electrons.
Wave-particle duality is one of the defining features of all quantum objects.
Like electrons and light, protons, neutrons and atoms behave like particles in some situations and like waves in others. Some researchers have even observed wave behavior in molecules. In 1999, researchers in Vienna, Austria observed an interference pattern for molecules made of 60 carbon atoms. Since then, they've continued to increase the size of the molecules in their experiments.
The first question is how big, how complex can such a quantum object be before quantum mechanics breaks down?
To me, this is just a technological question. We are now learning to see quantum effects for larger and larger objects, and I'm convinced that someday we will actually see them on an everyday scale.
No one knows where it'll break down or if it will break down at any point, and nobody can delineate a sharp boundary between the classical and the quantum worlds. This is a major open question.
So the electrons hit the screen one at a time like particles.
Right.
But when both slits are open, we get an interference pattern, like waves.
Even when we fire them one at a time.
Correct again.
Doesn't that strike you as a little weird? I mean, how can something that hits like a particle produce an interference pattern?
Does each electron go through both slits, like a water wave does?
All good questions.
I got it. If we want to know what the electrons are doing, why don't we just look at them?
Yeah.
Someone already thought of that.
Researchers in Tübingen in Germany placed measuring devices next to the slits. When they fired electrons at the slits, half of them went through the left slit and half went through the right.
See? Told ya. Problem solved.
Not so fast.
When the researchers looked at the screen, something had changed. The interference pattern was gone, replaced by a completely random distribution.
Measuring a system disturbs it, and so even though there's interference there when you're not looking at it, as soon as you look at which slit the electron has come through, it collapses into one of those two possibilities and looks like it's acting like a particle.
Many other experiments have also shown that measuring a quantum object disturbs it. It's as if the quantum world is resisting our attempts to unlock its mysteries.
In classical physics, when you measure something, that object stays the same. We're constantly being measured, and I don't change just because the light is shining on me right now. But in quantum physics, if you shine light on an object, you disturb it inevitably. So in particular, when we try to measure something in quantum physics, then what we're trying to measure will be gone.
Consider, for example, that you're trying to measure the position of a basketball. If you can use your eyes, the basketball's flying across the room, you can see where it is, and you don't disturb it. But now pretend you were blind, and all you could do was throw, say you had a pile of baseballs there. You're throwing the baseballs at the basketball, some of them will hit, they'll come back, they'll tell you where it was, but every time they hit, they kick it a little bit, and that ruins the information. And in quantum mechanics, you don't have the option of doing anything other than disturbing the system when you measure it.
So, we can't measure electrons or other quantum objects without disturbing them.
That's right.
You still haven't answered my question. What were the electrons actually doing between the source and the screen?
It depends on your interpretation, so we don't totally know.
The reason quantum theory seems so counterintuitive is that we have been brought up on classical physics.